part, but also the nilpotency part. That's a lot of what I was going to say anyway. So first of all, main work is done by postdoc Finn and the two projects of Alicia and Sophie. So they had to do all this. All right. So my viewpoint on the inverse problems is from a PD constraint optimization standpoint, and you've seen this. So minimize some objective functional. Just to get the notation, this is my state, this is the control, this is an abstractly written PD constraint. And for us, the control material parameters or the geometry of some. Not really a control setting, but still in the framework of PD constraint optimization. And then this is also something that Felix already said, right? For time-dependent problems, you like to set up the reduced objective functional, and then you can do things like joint gradient computation. You can do Newton's method and solve like KKT systems. My approach to this incomplete list of references was going through the Parallel Time website for the last 1.5 years, and there is really a lot of work on optimization and time. So these are some of the names, and I'm pretty sure I've forgotten stuff. It's kind of nice that so many of these people are actually here. Interesting. All right. I'll essentially talk about two applications. The first one is coming from medicine, where we have partners in the project that do 3D ultrasound of blood vessels. So what they do is they inject some contrast agent. Then they have time-resolved 3D ultrasound and see how that propagates through arteries into an organ. So it spreads out in capillaries, gets deoxygenized, goes back to the vein, and then circulation continues. So the goal here is ultimately treatment monitoring for cancer treatment, where tumors, of course, need oxygen. So what they do is they build a lot of blood vessels, a lot of capillaries to get all the nutrition they need. And then if you do chemotherapy, the first thing that gets destroyed is the blood vessels. So measuring this contrast agent propagation, so something that is a tumor in an organ, should reflect the amount of perfusion you have in your. So we're doing this. What we need to do is estimate two quantities in this first very, very simple model. So it's just transport of a contrast agent with larger vessels. And if you go to the capillaries that you don't resolve neither numerically nor in the images, this looks like diffusing. So this is the most straightforward, most simple model. Has a lot of downsides, and we'll come to that. And then this is the contrast agent. And the goal is to determine the diffusivity as well as the blood flow velocity. So this is the inverse problem that we're looking at. And we can now start a philosophical discussion because I do it the other way around. So we do optimize, then discretize. And there is reasons for this. And of course, there's disadvantages of this. We can talk about that. So what we have here is measurements coming from that ultrasound. So this is the concentration of the contrast agent. We have them essentially at discrete time points because the measurement device has a certain frequency with which it acquires images. So this is what we have to match. This is the constraint, and then we can, just as Felix explained, derive an adjoint equation. The adjoint variable is called P. which has a very similar structure. It's backward in time, and we can rigorously take care of these pointwise measurements by just placing time points at the measurement times, and then have sort of an inflow in time, or a jump in time at these points for the adjoint. All right, we have a divergence-free constraint for the flow velocity that we can take care of by projection, and then we get a gradient. And with that, we can now do an optimization algorithm, like a gradient descent method, like a Newton method, like whatever, that we can now, as this is all continuous, write down in function space. So we get a function space algorithm that converges in function space to the continuous solution. And then, of course, we need to discretize, so we have an inexact variant of this. And convergence theory tells us how to control the inexactness. That's sort of the other approach. We don't have a discrete adjoint, so we don't necessarily converge to the discrete, so we cannot run it until we reach the discrete optimal state. But then especially for the inverse problem, this is nothing that I really want, right? I'm more interested in the continued solution. There are, of course, discretization techniques where both approaches commute, so everything is fine. All right. So we've implemented this on typical test cases. So these are propagating contrast agent concentrations. We've implemented this in libfast, so we use STC or fast in parallel. So this is an artificial test case. This is actual measurement data from an animal experiment here. So this is contrast agent propagating to the organ here. And then we do the optimization. We do a nonlinear conjugate gradient method for this. And we get, for synthetic data with noise, very good relative errors. So this converges. This is not yet parallel in time, so this was a serial run. And I'll tell you why. And then we also did this for the actual measurement data, which typically is a bit more of a nightmare because you have to fight with a lot of things. But it also converges to something that looks reasonable. It has the right velocity, magnitudes, and the doctors were okay with that. Actually, the nice thing here is that they don't need high accuracy, right? So 20–30% relative error is totally fine. So this is, as I said, implemented in libfast for time discretization with a very, very simple hand-coded finite volume method. Does not really scale well. So what we're currently doing, with what Finn actually is doing, is coupling this to a finite volume code and running in space-time parallel. And just as yesterday evening, this worked for the first time. So we have now space-time parallel code, but no scaling yet. But soon. All right. There is two more things I want to say on this topic. The first one is, while the colleagues are fine with large error, they still want to know how uncertain this is. So for this, we need to do some uncertainty quantification, and we'll do this in a Bayesian inverse problem setting. The idea in a nutshell is, now you have random variables for everything. And you encode what you know about the problem in probability distributions. So what you know up front before you do any measurements, you put in a prior density. That might be knowledge of, like, say, physiologically meaningful flow velocities. In your likelihood function, you encode forward model or differential equation, but also what you know about noise measurements. And then Bayes' theorem gives you a posterior distribution that tells you what you know about your parameters interest given the measurements. And then you can do things with this posterior distribution. You can do point estimates, like the maximum, like finding the maximizer of this posterior distribution, which then is essentially the same thing as the optimization problem we've seen before, with suitable chosen norms. Or you can do sampling to explore this. And if you do sampling to explore this, you can compute like moments of the distribution. This is what I want to illustrate here with a very, very simple 1D problem. We try to estimate this flow velocity, this advection velocity. This is just a toy problem, of course, to check the implementation. We have measurements, we have measurement noise. We choose normal distributions here. This might or might not be for the application the right thing, but for this is choice here. The likelihood function measures the deviation from our forward model with a given velocity to the measurements. And for the prior, we just choose, well, we don't know a lot, so it's a rather flat prior with like centered around a wrong value. All right, and then Bayes' theorem tells us how the posterior looks. And then we can do sampling and find, for example, this histogram here of the posterior distribution that is nicely located around the true value. Like the width of this histogram tells you something about the answer. And the sampling is done by Markov chain Monte Carlo. For this, you need to often evaluate your forward model. And this, in this context, we do with FAST. And Thibault had this image on his slide. I explained it already. So we have fine STC sweeps and coarse STC sweeps, expensive parallel, cheap with a serial dependency. And then we iterate until convergence. What we also have is this predictor phase, because to compute values on the later time steps, you need to somehow initialize. And this also pipelines the algorithm. And there's different ways. In our context, we have an outer iteration, the sampling, and the inner iteration, the fast. So we can reuse the previous outer iteration to initialize the STC sweeps. And sometimes this works well. There is too much variation between the samples, it doesn't work anymore. At least it doesn't give you a benefit. And this is what we get for the simple toy example. So we have like a Markov chain. This is the sampled velocity. This is the sample number. There is a slight burn-in phase, and then it's centered around the true value. This is no surprise. So this is all Gaussian. This is all easy. This is 1D. This is cheap. Anyways, it's as a proof of concept and to understand what happens. This we ran in parallel on overly fine discretization, and we get speed up that drastically increase with this warm starting. And we have this hopefully now space-time parallel and can go to the actual 3D problem. So we'll see. I guess the message here is you have outer iterations, inner iterations. Try to reuse as much as information as possible. And the thing I did not do here is in the inner iteration, you shouldn't be more exact, more accurate than you actually need to be for the outer iteration. So this is over-resolving without end. I told you the model is kind of the simplest one, and it has downsides. Because if you think what happens, blood diffuses in the capillaries, but then it has to converge again to outflow. So modeling this with diffusion is not a good idea because that's negative diffusivity. You can, of course, computationally treat this somehow, but you can go also to a physiologically more meaningful model where you have an arterial and a venous concentration, as well as a conversion happening in the organ. So this is now no diffusion anymore, just transport in this two compartment. Nice thing about this is you can directly from this conversion function, you can compute measures for perfusion directly, which you cannot do in the advection. Initial reconstruction results look quite good. So this is also from synthetic data in 2D plus time. What happens here, there is contrast agent flowing along. There is conversion from arterial to venous blood happening somewhere here. And this is the arterial velocity. This is the venous one. Arrows are in the range of what we expected and what we need. Going to parallel in time is more involved because now there is no diffusion anymore. So we'll see how that goes. We have some experience. This is the second problem that I want to briefly talk about. Judith did talk about this on the last workshop, I think. This is reconstructing the bathymetry, so the bottom topography, in a shallow water equation model. So this is now nonlinear shallow water. I have this term here where the topography enters. We have measurements of the water height at some points, and we want to reconstruct this. Then this is the general objective function here. Deviation from measurements, potential final time term, plus some regularization. And as the derivative of this bathymetry enters, we should make sure that this is actually meaningful to compute, so we need some higher regularity. We don't need, well, it would be a control in L2, but we need it in H1. And again, same procedure, we can derive adjoint equations that now, as the equation is linear, are a bit ugly because coefficients here depend on the forward solution. This is still a linear equation, adjoint is always linear, but the coefficients are, at least, you need to view them as time dependent. And then we can assemble a gradient in L2, and to get a gradient in H1, you have to solve an additional elliptic here. So what we also don't do here is solving the coupled optimality system, but we really solve state and adjoint separately, compute a gradient, do a gradient step, and continue. And this is what comes out. So this is again for synthetic data. We have this Gaussian shape symmetry, distributed measurements everywhere, so very simple case. Some artificial noise on it, and nicely converging GS iteration. For the actual experiments that colleagues did at TU, we have water height measurements at 3 distinct sensor positions, which is really not a lot of information. Still, the reconstruction has a lot of error, but it's comparable or better than what so far is found in literature. So this is still like an 80%, 90% relative error, which apparently is what's achievable.
Where's the bump? That's all you want to know.
Well, the true bump is here. It sort of gets the peak, right? It gets the location, at least.
Keep you from running into it.
So to do this now parallel in time, we have to solve the two equations that behave very differently in principle. So we have the state equation, nonlinear shallow water, where we can treat nicely with this asymptotic parareal that you've heard about before. Can write the system, you slightly have to rewrite it but you get it in a form that fits here. And you nicely see the improved convergence. So this is the forward solution, the state solution on 10 time intervals, 10 time slices for standard parareal and for the asymptotic parareal variant, which we stopped at a reasonable accuracy. This is the error to the sequential solution. This is the increment. It's nicely done. So here you get some speed up at least. We don't want to do this for the adjoint because the adjoint not really has the structure, so it doesn't really fit. And then we have the freedom to treat it differently. And then the idea was, well, let's try para-exp. And sadly, due to this time dependency, I cannot just use para-exp. We need to use the nonlinear variant. Martin is not happy. It was an attempt. So this is the general form. We have a linear term, you have a nonlinear term for the para-exp. And in our setting, we get the linear term by some approximation, a fixed time or an average of this operator. And then the sort of defect to this approximation goes in the nonlinear, and then you have to iterate. And well, this is the error decay over the iterations. So convergence at the time slices doesn't look too good. But for the optimization, we don't really need to converge to this, right? We can stop early. And if we do this, there is at least a chance of getting some speed up. So don't oversolve the problem when you don't need the accuracy for the optimization. This is the preliminary results at the moment, and we're still working on this. What you see here is different discretizations for fine and coarse. And then we use serial adjoint, serial state. We use parareal for the forward equation, so the asymptotic parareal variant, and then different variants for the adjoint, serial, para-exp, and also parareal. And except for the para-exp variant, we get speed up. This is extremely expensive, and this is probably due to some issues in the implementation. So there is no need for this to be so expensive. There are 2 points. So we use Daedalus for this. 2 issues that we need to fix. That is, one is the evaluation of the right-hand side that might not be ideal how we do it. And the other is computation of the matrix exponential, which seems to be costly. But there is achievable speed up. On 8 cores, we get for the parareal variant a speed of 4.7, which is, I think, quite okay. And you cannot really coarsen anymore because at some point you get unstable. This also is work in progress. Hopefully these 2 issues are going to be solved at some point. All right. So there is not so many conclusions. There's a lot of to-dos and where, and I think I'll stop here.
Any questions? Martin?
Did you try the package of Stefan Güttel for the matrix exponential? This is a really good software.
Yeah, no, we haven't.
This is worthwhile. If everything else you try is going to be not as good, he really tuned that one. Download it.
Yeah, we talked to Stefan about
There's MATLAB. There's another implementation. Yeah. So yeah, this is what I actually started using because everything else I did was not good enough.
We talked to Stefan about the stopping criterion, but not about the matrix exponential. Yeah. We didn't realize that this was an issue yet. Okay. Thanks. All right.
Why isn't the adjoint equation good for the asymptotic parallel approach? It looks fine. It's got a fast part and a slow part.
Good.
Previous slide, I guess.
Well, this is the adjoint again, right?
Why do you see scale separation here?
Where do you see that?
Well, if you have scale separation in the forward equation, then you must have it in the adjoint equation as well. But you had an epsilon in the previous slide. Still there after
The
differential.
epsilon in the previous slide is just 1.
Oh, epsilon is 1. Oh, I missed that. Oh, okay, well, I'm surprised it works in the forward direction.
This was, I guess, quite some help by Juliana.
But the thing is that the G and the D should be rolled into the epsilon. Because if, yeah, G and D are bigger than 1, then maybe your epsilon is actually small. The wave speed is square root G times D.
Yeah.
So if that's big, then you have actually got a small epsilon.
So we tried this for the adjoint as well, but didn't really get much benefit.
Okay. Well, yeah, it's weird it works for one but not the other, I think. Not clear why. Any other questions? Josh?
With you're using the H1 roof map to get the gradient. But then it looked like you had a different weighting on the regularization than in the Reese map.
The regularization term shows up in the L2 gradient, right? Which is then on the right-hand side of that Reese map.
Okay. Do you notice an effect from not having a matched the coefficients in the H1 part of the gradient don't match with your Reese map? If this is like preconditioning.
I mean, we sort of, I think we need a bit to distinguish between the regularization term and the actual gradient in the function space setting, because the gradient is due to the inner product, which does not have these coefficients, right? These are coefficients controlling the sort of penalization of a gradient, which is different from prescribing the actual regularity for the quantity.
Okay, yeah. Maybe we can chat afterwards, because I've used that kind of regularization as a preconditioner, and I thought that was equivalent to what you've got here with the Reese map, but maybe I'm probably missing something. Yeah, have a chat.
That's all.
Any further questions? No. Okay, so thank you.
We're going to have a photo now on the stairs, so I'm going to grab Jade to come and take a photo of us, and I think they'll just set us off on the staircase. Don't vanish.
Just type it in. Leftover one. I know, we're getting worried.
This is mine.
I mean, I don't really dare to.
Promising, right? The backpacks are staggered. If we don't sit where our back is.
The discontinuity in that. Does it feel like that would happen all the time on the ocean? A ledge that goes backwards or something? Yeah.
You have a hard time parameterizing the
Student wants
the
marks. You should write it. But like, does it have a solution?
I'm so annoyed.
Yeah, you probably just end up with shock.
Right, cool.
Absolutely. You end it comes out.
No control. What I do is.
Yeah.
Somebody told me spins job. Then I just want to.
What is the matter?
I don't know.
My job is run.
USB unplug if you.
Yeah, no, everybody's. I
Go to admin, this fine will approve.
Yeah, USB on my plug.
Oh, thank you. I've just got the. Thanks.
good. Okay.
You're not allowed to touch any of them.
Yeah, she's even.
It's one of those things, it's one of those cases where the computer just kind of break down, like, in nonlinear. The message I got so far is students seem.
We have to go to.
should be able to receive email.
Okay, I
The
sent,
first received email about the.
it's, no worries. I sent the
You
email.
just went to the end there for the portal.
Yes, yeah. We are just slow.
Check the spam folder. No, what?
So there's that one. I was the one actually, it's quite nice, but a lot of knots there. Yeah, there's a lot of people flag bathing suits, like get it done. Yes, exactly. Well, it was an overcast day too, so it was pretty. That's okay. The beach there. That's Saturday. But it's still. Well, I'm not the shirt, I think, so. That's why I'm asking you before I was. Should I try it? I think somehow feeding on the people, and then you get more annoying. This is why I think it's current chop. Okay. Actually, it's her job. That's also short techniques like areas of the that's the market. Just back to the she has zero marks and she's I'm happy that she everyone I can say. Yeah, they're very high. The things we have to do something. Yeah. So you no. Yeah, so maybe that was the way it's stage. Yeah, the control variable. Those control variable. Yeah, but it's like you eliminate the state. These individual variables in the state. It's like and then let's say in this max,